Hi, I'm an old guy and I do maths. Today we're looking at how we graph this exponential function. And um, those of you who've seen my video on graphing unfamiliar functions will see that there are some parallels between that sort of general approach and what goes on here. So the first thing I'm going to try and do is figure out what the value of y is when I make x equals 0. So that simply means inserting 0 into this bracket here where x is. Now, there are a couple of things to beware of. This is negative 2 to this power, but look at how negative 2 is expressed. If we take a quick look over here, we've got what some people might see as the same thing, just written different ways, but it in fact is not. The order of operations in mathematics tells us that we must do the work with the indices before we do anything to this. Whereas this power here operates on the entire contents of this bracket. So let's put it this way. We can rewrite this as negative 1 times 2 to the 4, and that maybe makes this a little bit clearer. So in fact, this is negative 16, whereas this is negative 2 times negative 2 times negative 2 times negative 2, which is positive 16. So these are different, and we're dealing with this left-hand version here. So we have to be careful. Okay, that said, let's go to work. If we put 0 into this bracket, what we get is the following. We get negative 2 to the power of negative 2 plus 2. And I've gone to the trouble of writing this out in this form so it's really clear what's going on. Now, 2 to the power of negative 2 is 1 over 2 squared, which I hope you can see there, which is 1 over 4. And then I can apply the negative to that. So just have a look here. I've applied the negative to this, so negative 1 times 2 to the negative 2 is negative 1 times 1 over 2 squared, which equals 1/4. We add 2 to it and we get 7 over 4. So we get a pair of coordinates where x is equal to 0 and y is equal to 7 over 4. That gives us the y-intercept of this function. Right, so we've got that. The next thing that we're going to do is we're going to see if we can solve this for y equals 0. So basically, what value of x is going to give us 0 when we work our way through this function. Okay, let's go to work on that. So we're looking at trying to solve this. And what I've done here is I've sectioned off the 2, so it's really clear that this is negative 1 times 2 to the power of this. When I move this 2 over here to the other side of the equation, as I've done here, it becomes negative 2. Same story. And negative 2, or this 2 rather, is the equivalent of 2 to the power of 1. And we can solve this really simply using something that you'll probably have learned when you were first doing index equations, which is that if your bases are the same, you simply have to solve the equation that's created by this. In this case, it's a nice little linear equation. So 3x minus 2 equals 1. 3x therefore equals 3. And therefore, x equals 1. So we can put another coordinate in here, 1, 0. Now that's all very well. But what does this graph look like? We could join these dots in any manner that we choose. The basic graph of an exponential looks like this. It's a hockey stick shape. Now, obviously, something that looks exactly like that is not going to be very helpful here. So, what I'm going to do is I'm going to try just another couple of values, and what we might do is we might try 2 in here as a value of x. So I'll just find some space on this page and do that quickly. So that's negative 2 to the power of 3 times 2 minus 2 plus 2. Okay, so let's see what that works out to. So that is negative 2. I'm careful with that. 3 2's are 6 minus 2. That's to the 4 plus 2. Okay, so what have we got? Well, 2 to the power of 4 is 2, 4, 8, 16. 16 plus 2 is 18, but remember this, it's negative 16 plus 2, which gives us 14. So if we put 2 into this, this is wildly out of scale, we get a coordinate that's down here somewhere. And so we're now at a point where we can draw this thing with some degree of certainty. Now there's one other thing to consider. What happens over here? Well, you can put negative 1 into this and see what happens. If we do that, let me find some space here. Negative 2 to the power of negative 1 times 3 is negative 3 plus 2. So that is 2 to the power of negative 3. That is 1/8. So it is 1/8 that becomes negative because of this. So that's negative 1/8 plus 2. So this thing at negative 1 appears to bend over in this direction. And so it's a very, very safe bet that what we have is we have a graph that does the following. I'm just drawing in an asymptote, because if you do know anything about exponential graphs, what you'll realize is that this is usually an indication of where an asymptote lies. And indeed it proves to be true, because 7 over 4 is 3/4. This is going to be 1 7/8 up here at negative 1. And so this thing appears to turn quite tightly here and then run along it appears to turn quite abruptly here, it's quite a hard turn, and run along here with an asymptote at 2. Okay, so having gone through all of that, let's consider what has actually happened to an ordinary y equals, we'll say 2 to the x, a graph of y equals 2 to the x, when we do this to it. Well, the asymptote has moved from 0 up to positive 2. The negative here has driven a reflection in the y-axis. Well, not really, because we've moved the asymptote. But if we did not have this, that negative 2 would have simply flipped this graph. What this does is it changes other elements of the dynamic, and we'll look into this in further examples of this as we work through the business of graphing exponentials. But I hope that this was a good way to foster your understanding of this and to break into how it is you go about dealing with these. So thanks for watching, and I'll see you next time. Bye.